So at this point, let's assume that all the pre-processing has been finished, and now we are ready to run the linear regression on the data. So on slide 9, you can see we're reminded of the regression model that we're going to solve in this 3dDeconvolve step. And the command we can run to perform this with the actual data is the script rall_regress. And we'll run that in a moment, but let's start by going back to the command line and looking at this script. So in our current directory, we have this file here, rall_regress, and we can just cat that file. Cat, the Unix cat is short for catenate, so as you've seen with the prior commands, it just dumps the text of these files to the terminal window. So there's our command, and here's what we see in the file, and it's of course exactly what's on the handout slide. Some things to note about this: this is one single command, 3dDeconvolve command. It lasts all the way down here. That's a single command which is connected by these / characters, and those characters tell the shell that the command continues on the subsequent line. So if the shell reads this command, it'll see 3dDeconvolve -input rlvr plus a ridge, spaces, and then a /, and that tells it that this isn't the whole command. It continues on the next line, and it sees the next options, and then it sees another /, so it keeps knowing that it continues all the way down to -jobs2. A couple other little Unixy bits in here. Well, one thing to note about this /, if you open this in an editor, and just to pick one here, I'm going to say AFNI open -e. So I'll have this AFNI open look for an editor on my system, because on different systems you might have different editors. If you open this in a text editor, one of the important things to note is that there can't be any spaces after the /. If there's a space after it, the shell will not treat it as a line continuation, and that'll basically terminate the command and mess it up. And for example, if you accidentally typed a space at the end of this numstimts8 line, that will terminate the command after numstimts8, and the shell will probably give you an error message. For one, 3dDeconvolve will probably fail, and because we said there are 8 stimuli and we didn't give any. For another thing, the shell will then see -stim_1 as a new command, and it will probably say something like command not found. Like if I just dump this on the command line right now and hit enter, it says -stim_ command not found. It doesn't know a command with this name. So when you see something like this, that's not an AFNI error, that's a shell error, and that usually means that you have some script where you've probably got spaces after a line continuation character. But in an editor, you can't see them. So as long as I'm babbling about that, I'll just go on a side view and note that if you're unsure or you want to find out where they might be, if you do have some, well, actually, let me open it up again and add a couple here. So there. Now this has spaces here, and I'll save it. If I run, if I want to check this now, I can run file tool -test -infile, and now it's rall_regress. And file tool will tell me there's a bad / on line 6, and I've got spaces after it. So then you have to you have to fix that in an editor. I'll go back here and delete the spaces and save it, and I'll run file tool again, and it's happy. No bad characters. It's a Unix file type. Note that in the output here, so here's file tool whining about it. It actually tells you it can fix that. consider this command. If you add a prefix option, it will try to fix some of the issues it finds. Anyway, that's just a side note, but that's often very useful. Anyway, so back to our script here. Now let's take the this is the main part of what we want to do in this class. We want to understand the linear regression and look at how look at what the regression model looks like and how it's fit to the data. So let's just go through this in pieces. The input is rall_vr plus a reg. So note we're supposed to have 3 runs of data, right? And we'd have 3 files here. Just to really save space on the handout, unfortunately, we've just put this into one data set instead of 3. So we might want to make a note of what pre-processing has actually happened on this data set. Has it been t-shifted? Has it been registered? Has it been blurred, scaled? All these possible pre-processing options. Remember, this course is just a simple example, so we didn't do everything to it. And you might note that since this ends in _vr, it's probably been volume registered. But let's do 3dInfo on rall_vr plus a reg. And when you run 3dInfo on it, it doesn't show all the information. Like, it shows there are 450 time points, but it's only showing you information about 3 of them. That's okay. We don't need to see everything, but we know that this is 3 runs of data, and we can guess that, remember, there were 152 time points, of which we had planned to remove the first 2. So that would put us at 450 time points across all 3 runs. And that's what indeed has been done here. The history for this file includes just 2 commands, 3dTcat prefix rall. Let me make this window wider temporarily. Dash prefix rall, and then the input is pb00 for ft. So we'll see that actually in a later class. This is just grabbing some of the first data sets created by AFNI-proc, the AFNI-proc script. But this has just been run through the tcat step, which just removed the first 2 time points per run. So this is input 1, run 2, run 3, and put them all together into a data set called rall. And then we just ran 3dVolreg on it with base image 2. So out of the 3 runs, out of 450 time points, the 3rd volume of the first run is used for registration. So the base 0, 1, base 2, time point 2 is the registration base. And 3dVolreg was used to align all the API volumes to that. The output data set from 3dVolreg is rall_vr, so that's what we're looking at. And then it also stored the motion parameters in motion.1d. So almost no pre-processing has been done. No t-shift, no blur, no scale. This has only been volume registered. And that's fine. We're just focused on the linear regression here, but we should know what data we're starting with. And if we type ls again in this directory, note that we do have this motion.1d time series. I'm going to shrink my window back down, type ls again. So now that as long as we're mentioning that, we might as well look at what motion.1d is. This will be referenced from the registration class, but so at each time point, remember 3dVolreg does 6 parameter affine registration that includes 3 shifts and 3 rotations to align each volume to a base volume. And our base volume was index 2. If you look at this motion, you can open it in an editor if you want to. You can use AFNI open-E, or you can cat it. I'll just use less. Remember, with less, you use Q to quit. But it's just a text file with 6 columns and they're the 6 parameters: 3 rotations, 3 shifts. And one thing you notice that's interesting here is that row 3, so this is time index 0, 1, 2. Time index 2 has all zeros there. Why? Well, this shows the parameter is used to register time index 2 to the base volume, but the base volume is time index 2, so fortunately 3dVolreg did not work too hard to do that registration. So all the parameters are 0, and that's what we're seeing here. Typically, though, you don't plot a motion parameter time series like this. You'll typically do something like 1D plot dash volreg, and that volreg option just labels the axes a little more nicely since it assumes the output from 3dVolreg. And it's nice to add SCP SCL for separate scaling. And there we go. These are 3 runs of motion parameters produced by 3dVolreg. We see the roll pitch and the yaw on the bottom. So this is column 0 from the bottom. It's column 0, 1, 2, 3, 4, 5 for that 6 column 5 file. And then I to S, right to left, A to P shifts. You see these big jumps here. That's for a run break. This is 3 runs. So just looking at this, usually there's a registration break across runs as the subject relaxes or shifts their position a little bit when the scanner is off. That's okay. We don't count that really as a motion, as long as they don't move enough to throw off, to introduce a big distortion difference between the runs. So you wouldn't want to re-shim between the runs. That'll cause the distortion difference. But so as long as they didn't move enough where the shimming is messed up, we don't really care too much about these jumps. So we're not going to actually model this. We'll typically model the motion parameters separately per run. Anyway, so run 1, run 2, and run 3 here. There are some spikes in this. There's a spike down here, a spike over here. Remember, this is that 2-degree head rotation, a pitch. Notice none of the other axes even really show that. That's because it wasn't quite the typical 3D rotation. We just literally did a 2-degree pitch. We had to fake that. The bad subject didn't move enough for a good class demonstration, so we added our own. But anyway, so these are the motion parameters. So getting back to the actual script now, it's a 3dDeconvolve command, and our input is that our all VR dataset. So that's all 3 runs and volume registered, and that's it. Now, how are we going to model this? What do we tell 3dDeconvolve about this dataset in order to model it? The first option up here is -polart1. So that's telling 3dDeconvolve to measure, to model the slow scanner drifts, with a linear trend in each run. Polart1 says to use a first-degree polynomial to model the drifts with. So in a later class, we'll do a more grown-up version of this, which will use a higher polart. But for this simple case, we're just starting with using a linear trend just to keep things quick and easy. So that will use 2 polynomial terms, a constant term and a linear drift per run. Since there are 3 runs, this will end up using 6 parameters. Then we have a concat option here with its parameters. We put all 3 runs into a single data set. Again, that was mostly to save slide space, but typically we'll give 3 data sets here. Because we only gave 1 data set on the command line and there are 3 runs, we need to tell 3dDeconvolve that there are 3 runs and where the run breaks are. So we use this concat option here to do that. It uses the syntax 1D colon just to say that this is a simple 1D formatted file, but specified on the command line, and the values in there are just just the indices where the runs begin. So out of 450 time points, run indices 0 through 449. Run 1 starts at index 0, run 2 starts there, run 3 starts there. And so 3dDeconvolve knows that there are 3 runs now and when they start and end. So now we have our input and we know how many runs there are and we know how to model the baseline drifts. Now we specify more terms in the model. So we're going to add 8 more terms to our regression model, and then the first 2 we add are the actual stimulus classes that we care about. This is the whole reason we're running the regression. This is the whole reason we're going to do a group analysis, is based on these 2 parameters. So we give to 3dDeconvolve the event times specified, for example, with stim times 1 in the file stim_av1viz.txt. So if we go to our shell, you'll notice we have stim av1 and stim av2.txt. Those are the event times for those 2 conditions. If we cat stim av1, this is what you see. And the format of this file, we'll just stick to a very basic format here. We don't have modulators and we don't have durations. There are 3 runs, and therefore this file has 3 rows. This is called the local times format, but that means that all of these event times are with respect to the local run. So these are times for run 1, these are times for run 2, these are times for run 3. These are times in seconds from the beginning of the run in terms of the data that 3dDeconvolve command knows about. So for one crucial detail here is that we removed 2 time points from our data. That's to say that from the scanner we removed 4 seconds of data. Now, does the scanner account for dummy volumes? Does it account for that dummy time or the pre-steady state time automatically? When does the presentation software start? During the pre-steady state time or after it? The answer is that depends on your setup. It depends on how the presentation software is connected to the scanner. Does the scanner give a start signal to the presentation software or what? In our case, we just had to know that well, actually, I don't even know how it was for Mike. This is Mike Beauchamp's lab, but a common case is that your presentation software starts during the pre-steady state time, which means in our case we'd have to account for the 4 seconds of time between when the scanner starts and when we want our stimuli to start. So 3dDeconvolve doesn't know about that 4 seconds of data, doesn't know about that time. So at the scanner, my first visual reliable event did not start at time 60, it started at time 64. So I had to remove 4 seconds from all of my event times to create this file because we had decided we were deleting 4 seconds of data from the beginning of each run, 2 volumes. Again, typically it's more than that, but that's what we are using for an example here. So if you for some reason have a time timing that is associated with the scanner times, and you need to subtract a constant from each event in your file, you could run something like timing tool dash, well, let's do hweb and get help from our, instead of terminal help, we'll get it from in the web browser. And here's the timing tool help, and we start off with all these examples. Here, example 2 shows how to subtract time from each from your stimulus timing files. And that all we're doing is adding offset to each file. So we'll input a timing file, we'll add offset. In our case, it'll be -4 to subtract 4 seconds, and then we'll write a new timing file. So you could just run this across all of your timing files if you needed to. Anyway, it's on the researcher to know whether they have to adjust these times. And if these times do not match the actual data, you're in trouble. Commonly fast event designs are used. If you're off by 10 or 12 seconds, your results are just garbage. So you have to be sure of this ahead of time. Once you know whether you need to adjust once you know if you need to adjust the times, it's very easy to do, but you need to know and you need to do it correctly. But given that, now we have 3 runs, that each of which are 150 time points of 2 seconds, so each run is 300 seconds long. And the first event of the visual reliable stimulus started 60 seconds into the first run. Second event, third event, fourth, fifth in the first run. You notice that the first event didn't start for a whole minute. 60 seconds. These values don't have to be integers, and they're not TRs, they're times in seconds, but they could be 58.36 seconds as well. It doesn't have to be an integer. But if we cat the AV2 odd dot text, we'll capture the other times. Going back to the slide, remember our events were basically 20 seconds of stimulus and then 10 seconds of fixation. So there should be 30 seconds between the onsets of these events. And that's what you see here. So run 1 must have started with an auditory reliable, auditory, visual, 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 auditory, visual. So basically sorting these things by eye. But now 3dDeconvolve, when it reads this file, it knows the onsets of these events. Beyond that, we have to tell it how we want it to model them. So coming back to the command, if for our visual task, we tell it we want to model each single event, each single stimulus response with a block 20,1 function. That's not BLOCK is not saying it's a block design, even though it is in this case. It doesn't have to be. BLOCK is a very specific model function in 3dDeconvolve with a specific shape. Beyond that, we tell it that each event is 20 seconds long. So it's going to take, the block function is actually like a 15-second curve. It's a little longer than GAM, but it's 3dDeconvolve will take that 15-second curve and convolve it with a 20-second boxcar. So that 20-second boxcar says this is how long the stimulus was on for. And it will convolve them together and give you a 35-second, 20 plus 15-second response curve, and we tell it to make that curve height 1. So just a quick view of I'll keep opening a new window. Maybe I'll leave this around, but just so we can keep this window where it was. If I quickly look at 3dDeconvolve -help, and you can do the -h web if you want. I'll just pipe the help through less in this case, and I'll search for in less. I can do a slash to search for BLOCK to find the definition, and here's the definition for it. So it's a 1-parameter stimulus of duration d, and the p is the height of it, and it shows you how it's modeled. T to the q, e to the negative t, q times q q to the q. Is that right? E to the negative q. So this is the shape of the curve for the different p's and q's Here in this case, P is our height and Q is either 4 or 5. Anyway, so you can see what that means. If you want to plot this, I'll quickly show you another thing. Timing tool, which messes around with timing files, has an option, help basis. At the end of that, it babbles about the various basis functions, like block D, comma P, tells you the duration and the peak and things like that, and how these things compare is really what it cares about. And if you run this quick 3dDeconvolve command, you can say I have 200 time points at a TR of 0.1 seconds, so 20 seconds of time, and polar -1, so no polar. I just want to look at the shapes of these 4 curves. So I have, for each of these, I have like an event at time 0, and I give the different model functions, and I want to just look at them. So if I run this, it produces a curve. It produces an output x.xmat.1d, the matrix for this, and then going back up to this help, now I can plot it with the more complicated, the more simple version. I'll just grab the simple one. Good enough for here. So if I dump the simple one here, these are the curves. So, and what we're looking at, the bottom one is a GAM, the next one up is the wave. The next one up is, so the red one is wave, the black is GAM, the red is wave, the green one is block 1. That's for a 1 second event, so this is a fairly instantaneous block curve. And then SPMG3, there are 3 parameters. The canonical, the first derivative, and then the dispersion curve. Anyway, so that's a quick way to look at what the actual single event curve looks like. So if we did something like this and used block 20,1, we could see what this really looks like. Of course, we're going to do that in a few seconds here, so we don't need to run that separately. So we give our event times to 3dDeconvolve. We tell it how to model them, and we have the audio times as well, and we're using the same model. And then we give it a label for each of these. And so in the output from 3dDeconvolve, anything for visual reliable will be called VREL, and audio reliable auditory reliable will be AREL. And then we have 8 more stimulus inputs. Stim file means we're not going to do any convolution. We're telling 3dDeconvolve to use the file as is as a regressor. And you can see we're giving the 6 motion parameters here: roll, pitch, yaw, DSDL, DP. So that's for column 0, 1, 2, 3, 4, 5 in the motion.1d file that we plotted earlier. Just a quick reminder, 1d plot. We still have the command here, so I was able to retrieve it quickly, and there we go. So these are being specified as regressors of no interest here. Actually, the regressor of no interest is the stim base part. We're telling 3dDeconvolve to put them in the baseline. That doesn't change the statistics. It just it tells 3dDeconvolve that, like for the full fstat, the fstat will be computed where these motion and polynomial terms are in the baseline. By default, also, it's not going to output beta weights for these terms. We'd have to ask for that separately if we wanted them. But anyway, that's our model. In this simple case, we have 3 runs of 450 time points, where these are the run breaks. We're going to model, so our X matrix will be composed of linear polar terms, polynomial terms per run. It'll be comprised of the 2 idealized response curves by modeling these events with block 20,1. Again, if the event is the block curve is like a 15-second curve. And when we tell 3dDeconvolve to model it with a P of 20, so if the duration is 20 seconds, then it's going to 3dDeconvolve will convolve the 15-second block curve with a 20-second top hat, and we'll get a 35-second response curve for each event. And we'll use the exact same response curve for every stimulus. That's our fixed shape regression model. And then again, the stim files, the motion, these are the actual regressors. So now let's actually run this script. Again, are all regresses in the current directory. It doesn't take too long to run. We could have started it earlier, but we'll just start it right now. And I'll take a few moments to actually look at the text output to the screen. So scrolling back up here to where we ran the command. It runs this command, then here's the text output from 3dDeconvolve. It gives you the version, how much memory is initially allocated, tells you it's loading the data set. It ended up allocating almost 200 megabytes of data. The input pole art is 1. And it whines about that a little bit. It says the runs are 300 seconds, so it recommends using a cubic polynomial for slow trend modeling. We'll do that in the grown-up version of this analysis. Right now we're just keeping it simple with the linear trend modeling. And then it finds the stimulus times for our 2 regressors of interest. Babbles about that a little bit. We have 450 time points, a total of 14 parameters. Let's make sure we agree with that. So remember, our model is comprised of polar linear polynomial trend modeling per run. So the linear model is a constant term plus the linear trend. So that's 2 terms times 3 runs. So this is 6 regressors right here. And then 7 and 8, and then 6 more for motion is 14. So we see 14 parameters in the X matrix. 12 are baseline, 6 polynomials, 6 motion, and 2 are regressors of interest. Then it gives us some memory information. It says it wrote the matrix to rall underscore x.xmat.1d, so that's our regression matrix. Talks about using how you could run 3D REML fit, and actually that it saves this command to a text file that you could run if you wanted to run the REML version of the regression with the generalized least squares using the ARMA 1.1 model. Then it looks at the signal, it looks at the pieces of the matrix and tells you if the condition numbers seem suspicious. The condition number is the ratio of the largest to the smallest eigenvalue. So if the condition number gets large, that means small changes in the data can produce larger, surprisingly perhaps, large changes in the results. If the condition number gets very large, that suggests you're more borderline on multicollinearity. In this case, they're all small numbers. Life is good. So it says we have this option at the bottom here, jobs 2. So 3dDeconvolve is going to fork an extra process and use 2 CPUs. If your computer, if you're running a larger command and you have 10 CPUs at your disposal, you could bump that up to job 6 or jobs 8. Don't use everything, but and share with your friends. But you can bump that up as you see fit. This is the main loop that it outputs as it's running a pacifier, so you know the program hasn't just died on you. So it outputs these 50 digits 0 through 9 40 digits while it's going through 50 digits 5 times. Oh my goodness, I'm losing my head here. just so you know the program is still running. That sometimes takes a long time. Here it's pretty quick. Waits for the kids to finish up the extra jobs, and then outputs some information about the FDR values. If the false discovery rate values are too too big, that means basically nothing seems to be, you don't have enough significant voxels in that volume. In this case, they're tiny. The results have very large t-values and small p-values, say. And the output was written to rallfunkaridge.head and brick. So that's great. A couple other things to note here. We have a GLT, a symbolic GLT, to compare visual reliable to auditory reliable, and that's a subtraction in this case. One of these minus one of these. It's using the labels that were specified up above. And we'll call this GLT V minus A. So the V minus A in the data set refers to this subtraction. We'll get t-stats output for everything. We'll save our X matrix in rall underscore x.xmat.1d. We saw text mentioning that to us. It'll save a JPEG version of that if we want to see it. It'll save a fit time series in rall fits and a bucket time series. In this case, in AFNI, the term bucket just means a data set where many things can be thrown into it. They don't have to be all of the same thing. Like the EPI time series is a data set where all the volumes are EPI volumes. The bucket data set here has beta weights, it has t-stats, it has f-stats, it has GLTs, so it's a mixture. And now when I type ls, I see some of this stuff output. I'll type ls-ltr just to sort by time with new stuff at the bottom so we can see what it produced. So here's the script we ran. It dumped any warning messages that were also on the screen, but it saved them in a text file. Here's our JPEG. We can use, it's a JPEG. You can view it however you want to. I'll use an AFNI image viewer just for kicks. So there's a grayscale form of the regression matrix. We've got baseline terms, regressors of interest, and motion. I'm not going to focus on this because I'm not thrilled with this format. But black is big in this case. So it goes smallest to largest. This is the constant term, the linear drift for run 1, constant linear for run 2, and the same for run 3. But if we wanted to look at this in a more practical way, we might view this using 1D plot dash separate scale on that rlx.xmat.1d file. So this is the text form of that file. That's the text form of the regression matrix. If we plot that, this is what we want to understand. So we told 3dDeconvolve how to model our data, the model that we want to use to fit to the data. And so it's going to do its best job with the least squares fit, but it's our job to tell it how to create the model. So we told it use polar 1. So that's what we see at the bottom. Here's the constant polynomial term from run 1, the linear drift from run 1, and then zeros everywhere else. And then the green and the blue here are the constant and linear drift terms for run 2. 0, 1, 0 is the constant term for run 2, and then 0, -1 up to 1, back to 0 is the linear term for run 2, and then similarly for run 3. Next come our two regressors of interest. On these two lines here, we have first the visual reliable. Remember, the first event didn't happen until 1 minute into the first run. In that minute, we had audio reliable events, stimulus events. So there's the visual reliable idealized response curve and the auditory reliable idealized response curve. And then after that, we have our motion terms. 6 lines of motion, which you see here. And note that this is exactly what we had. If I do Control Z and put this in the background briefly and repeat a 1D plot and go back and look for our behave go back and look for our motion.1d file, if we plot that, these are the motion parameters. And that's exactly what we see in here. The colors aren't the same. So the black down on the bottom here is the same as the red curve. This red curve matches the green curve in here, and so on. But these are the same motion parameters that we have in the X matrix. I could make them look a little more consistent by making these of the same height and width, just for kicks. And now you can see the match better. Anyway, I'll close this. So this is our regression matrix. Anything that the data that is not shown or represented in this regression matrix will not be well fit. So if there are actually cubic trends, cubic drifts in the data, they will not be well modeled by the linear ones and will do a poorer job of fitting everything else. So it is our job to come up with the model that we want to use to model the data, and it's 3dDeconvolve's job to actually apply that model, or 3D-RemelFit's job to apply the model. So the output of this is now beta weights. And what are the beta weights? The beta weights are, for one particular voxel, how much do we multiply each regressor by to get the best fit to that data. So again, this is the X matrix that we're looking at here. And we want to come up with beta weights so that the beta weights are numbers we can multiply each regressor by to get as close to the data as possible, such that the residuals, the epsilon time series for that voxel, is minimal in the sense of the minimal least squares. So the sum of the squares of epsilon can't be any lower than the one that gives those beta weights. Now, what beta weights do we get? To look at that, we can actually look at the results in AFNI. So I'll stop here, I'll break the video here, and then we can continue on looking at the results in AFNI in the next one.